So, welcome to the session on post-quantum cryptography. We have 3 talks, and the first talk has a large list of authors: Mingxing Chen, Andreas Hulsing, Joost Reineveld, Simona and Peter Schwaber. And Joost Reineveld is going to give the talk. So, thanks.
Okay, so I'm going to talk about building MQ-based signatures from 5-pass MQ-based identification schemes. Yeah, let's just start. Why do we want to do this? So the problem is we want to have signatures in a post-quantum setting. The current signature schemes are not going to cut it when quantum computers arise, and we want to have a secure signature scheme. Basically, we want 2 things. We want security arguments for these schemes so that we know that we can trust them, and we want them to be acceptably fast and reasonably small in terms of signatures and key sizes. You can debate about what is acceptable here, but let's just assume we have some notion of what is, for now, let's just assume we have acceptable as a term. There's a bunch of people that have already come up with solutions. There's conservative hash-based signature schemes. There's lattice-based schemes. There are some schemes based on MQ. They all have upsides and downsides. We're going to focus on MQ here. And for MQ, the current situation is that the stuff that's out there, the security is not very clear. Many of them have been broken. There's some that still stand. And we're going to try and base a signature scheme on MQ that is a bit more conservative. But before we get to that, let's first go for the general construction. And an overview of what we're going to do in this work. First, we're going to, in general, transform 5-pass identification schemes into signature schemes. To do this, we extend the Fiat-Shamir transformation. This is traditionally defined for classical IDSs. I'll talk about it later in a bit. Then we'll show that an earlier attempt to do exactly this did not suffice. And then we're going to look at a specific application of this, and then look at an MQ-based signature scheme that you can obtain by using this transformation. This signature scheme bases its hardness on the MQ problem, which I'll also introduce in a bit. And then we instantiate and implement and show how fast this is and how big it is. There's some footnotes. There's stuff we don't do. The reduction is in the random oracle model and not in the QROM. The proof is also non-tight. There is a reduction, but yeah, it's not tight. So let's get started with some preliminaries. The canonical identification scheme, so this is the typical 3-pass identification scheme. Your prover commits to some random value using the secret key, sends these commits over to the verifier. He comes up with challenges. The prover computes responses based on the challenge that he gets and sends these over. The verifier checks if these responses match what he would expect based on the commits and the challenges. Or the commit and the challenge. This is the traditional setting. And then what do we require of this identification scheme? We require it to be passively secure. And we define security in terms of soundness, which means the probability that the adversary can convince a verifier should be small. So only a real prover that knows the secret key can convince a verifier. And we also want it to be honest verifier zero knowledge, so that basically the verifier could simulate the entire transcript, showing that he does not know the secret, and he's able to compute one of these conversations without actually knowing the secret. if you go from the bottom up, this is a convincing way to show that your secret is not actually leaking. So for soundness, there is some chance that the adversary can guess right. We define this with the soundness error kappa. This should be small enough so that, yeah, this is negligible to some extent, but for one round of the IDS, this would typically be like a half or 2/3, something along those lines. But we'll come back to that. So how do we turn this into signatures? You apply the Fiat-Shamir transform, but before doing that, we first need to get rid of the soundness error. I just mentioned it. Typically, this is a number of the order of half or 2/3. And by composing a lot of instances of this IDS in parallel, we can reduce this, because basically you're multiplying the soundness error for each parallel composition that you're doing. So you compose until you get to a negligible level of error in your security parameter K. And then we transform this into signatures. The end result is non-interactive. So before we had this two-party thing where you had a prover and a verifier. Now we just want to have a prover that computes the signature. So the signer is the prover. And he uses some hash function or some function H to compute challenges, which he then responds to, and this conversation ends up being the signature. And we want to generalize this, because this is the classical 3-pass setting, but by scaling it up to 5-pass, you can benefit from a lower soundness error. Typically, the 3-pass schemes would have a higher soundness error, and then you would need to have more in composition, but generalizing this to a different setting could make for a more efficient scheme that has less rounds, so a smaller transcript and easier to compute. But then the current Fiat-Shamir transform works on like the canonical IDS that I just showed. So that's where we're aiming at now. So as I mentioned before, there was an earlier attempt to do this. In 2012, Asiacrypt, a paper appeared that defined n soundness to apply a Fiat-Shamir transform to any 2n+1 pass signature scheme. And basically what they did, they said if you have two transcripts that agree up to the last challenge, and then you can extract the secret key, then you have this property called n soundness, and then the transform applied. We show that this actually does not gain you anything, because all the schemes where this would apply can be transformed back to 3-pass. So you can restructure such an IDS. Basically what we're doing is we show that if you have some 3-pass IDS, you can prove honest verifier zero knowledge by taking, for example, if you're going from a 5-pass, you would combine the first 3 messages into one, then get a 3-pass scheme. And for special soundness, you would show that you can extract from some 3-pass scheme using the extractor that this 5-pass scheme would provide. Basically, you're proving an equivalent 3-pass scheme based on an existing 5-pass scheme that has this property, which would be great, because then you could apply the traditional Fiat-Shamir transform to this resulting 3-pass scheme. Only none of the existing 5-pass or 7-pass schemes or whatever pass schemes apply, because they don't satisfy this condition. There's no such extractor that from 2 of these transcripts you can actually get the secret key. Then the authors ended up fixing it in the journal version of this paper this year. And they redefined, and now it doesn't reduce the 3-pass anymore, but still it does not apply to existing schemes. So that's the gap where our work comes in. What we're doing is we're doing a Fiat-Shamir transform for specifically 5-pass as opposed to 2n+1 pass. And we're restricting it to a very specific instance. So we're looking at schemes that have to form the first challenge. So if you're doing 5-pass, you typically have 2 of these challenge phases. For the first challenge phase, you take a challenge from some queue, so that is a parameter you define, and the second one is a binary challenge. So it's either a 0 or 1. That restricts the setting we're in. So it's not a general 5-pass scheme, but one that confines to these limitations. And then we're going to prove that this is CMA using an unfortunately. Anyway, we're going to prove this using a dedicated instance of the forking lemma specifically tailored to this Q2 IDS constraint. Basically, we assume a successful forgery, Then we generate 4 signatures following a pattern on like these specific challenges. You would have, for the first challenge, you would have one that agrees and one that disagrees, and then for the second one also one that agrees and disagrees. This is a very specific pattern for these that follows from the fact that this is a binary second challenge. And then we can obtain 4 of these traces and use an extractor to show that this works. This would apply to like IDSs that follow this pattern. Now, before going into the very specific instance that we're applying this to, because this looks like we have some instance in mind where this condition holds, let's first look at the context of this, the hardness problem, the hard problem that we're basing this on. That's the multivariate quadratics, the MQ problem. And it's defined as follows. We take a function family MQ over some M, N, and FQ. And all of these are polynomials that are quadratic. So basically they consist of quadratic terms and linear terms, and they have coefficients. And together all these coefficients make up an instance of such a problem. So basically the problem is given some output of this function family. For some input, you need to find the pre-image x that went into it. So basically, you're solving a system of equations where you have coefficients a and b, and you input the x's and then get the y's out. Then going back, if you have this y vector, you cannot easily find the x's. That's in a nutshell the hard problem that's behind this. And then we're looking at an identification scheme that uses this. Now, I'm not expecting you to read this protocol in detail, but just to get a general idea of what this IDS would look like. Well, it looks like this 5-pass setting that we're looking for. It has the first challenge alpha comes from some FQ, and then the second challenge CH2 comes from like the set 0, 1, so that's a binary challenge. First, the prover commits to some randomly chosen vectors from FQN, commits to these response to the challenge alpha. There's an evaluation of f there. That's this MQ problem that we just discussed. And there's also G up there, which is a variant on this. I'll come back to that on the next slide. Basically, this follows exactly the pattern that we just looked at, like the assumptions that the proof would hold for. So this is the scheme that we're going to look at. So how does the scheme work in a bit more detail? It relies on just the MQ problem. Typically, schemes based on the MQ problem would also have other related problems, which typically introduce the security problems that we've seen with other schemes based on this problem. They would rely on isomorphism of polynomials or other related problems, and then people would claim that they are based on this MQ problem, but there's also related problems, and these typically lead to attacks. While for this scheme, it's only this MQ problem that we're looking at, because that's the only thing we're evaluating here. And what Sakamoto et al. Did for this IDS, they showed that you can take this MQ problem and split it into parts, split the secret into parts, and then using some bilinear function that I won't go into detail here, but this allows them to split it in such a way that you can either reveal these 3 factors or the other 3 factors, which basically give you the responses of the prover here. And this shows that you can have some sort of proof where you're proving knowledge of either one half of the secret without revealing the other half, because the split is random and does not allow you to compute the other half of this secret S. I won't go into detail on this any further, but that's the general idea. So what do we do with this? Basically, now we build a signature scheme out of this by applying the Fiat-Shamir transform we saw earlier. Start by sampling some seed and picking a random secret key value that serves as the X for our problem F. Basically, you had this F, this X of input elements that would go into the capital F to evaluate to get to some Y. Here, Sk is the X and Pk is the Y. And that instance is basically our key. and then we take some C to sample f from, because f is this large set of all the coefficients, and it would be very impractical to have this as part of your key, so you would typically just have a C to expand this from. You could also have this as a system parameter, but yeah, that's not necessarily a reason to do that instead of just having it as part of your key. So what does signing look like? We sign some random digest d over m, so we like hash it and then use this as an input bit string, and then we perform r rounds of this IDS. Basically, we're doing this VIASM transform where we first parallelized this IDS. We've made a composition of r instances of the identification scheme, and this consists of doing two r commits, because you saw earlier that there's two commits per instance of this, and there's also two r evaluations of this MQ function, because there's f and there's g up there. I'm not sure how legible this is, but people in the back will just have to believe me on this. So there's two r commits, some multiplications in FQ for this challenge alpha, and then two r MQ evaluations. And in terms of how much effort this is, like where does the computation go, these commits are just applications of hash functions or some string bit commitment. But these two r evaluations of MQ, that's the costly part. And then, of course, there's some size, so we can play a few tricks to reduce the signature size. That's typically the bottleneck here. You don't want to have a very large signatures, and you want to somehow limit this to as much as you can. And you can do this in a couple ways. A few of the tricks we pull is you only include the necessary commits. Basically, the verifier reconstructs one of the two commits, and the other one you would need to supply, but the one that the verifier is reconstructing anyway, you wouldn't need to make part of the signature. And you could commit to seeds. That's instead of committing to like full sets of random data, you could commit to some seed that produces this random data and then later reveal the seed. For our parameters, that last trick didn't apply, but in general, it could work. And then how does verifying work? Basically, bottom up of the same story. You reconstruct the digest and this system parameter f, because the seed is part of the public key. Anyone can just reconstruct f. You reconstruct the challenges from whatever is part of the signature, because the prover used the message and is commits to generate the challenges. You verify the responses. You reconstruct the missing commits that we omitted by only including the necessary ones. And then you check if the commits that were omitted actually match whatever checksum or hash or whatever was included to account for like leaving out half of these. And then there's a bunch of parameters that we leave out that we've omitted to give instances of so far. So there's k, the security parameter, and there's n and m, the dimensions of our MQ problem, where n is the number of inputs and m is the number of outputs. We're doing this over some finite field FQ. There's a commit function, there's a bunch of hash functions, and there's random number generators. So let's now look at a specific instance of this. So MQDSS3164 is what we define as the instance in our work. For some security parameter, k is 256. This results in the general post-quantum security of 128-bit. And then we have some soundness error kappa that depends on q, so that makes it important to choose a q that is not 2. Typically, people would choose q as 2 for one of these problems, but then if you increase q, kappa declines, so you would need to have less of these composed IDSs in parallel, which makes it interesting to choose a slightly larger q. So we go for q is 31, and n and m are 64. These are restricted by attacks that would be feasible if you have lower n and m, or you would have them vary, because you could have a slightly larger n and a slightly smaller m, for example, or the other way around. But they are also an artifact of wanting to choose nice parameters for code. I'll come back to that briefly in a second. And then there's a bunch of functions that you would need. We have some commitments, some hashes, some pseudo-random number generators. All of this is not really much of a factor in terms of how fast the scheme becomes. So we use the reasonable choice of just going with catch-up functions here. So to summarize, the signature then contains some R to have this randomized message digest, some hash over these commits that we're leaving out, and then for each of the rounds, there's going to be 269 of those. We have these response vectors T, E, and R, and one of the commits that you would need to include, that the verifier cannot reconstruct, so you would need to include half of them, which comes down to roughly 40 kilobytes of signature size. So a slightly more detailed look at how this MQ problem works. So going from fx to x should be hard, but from x to fx is something we do a bunch of times during the evaluation of this, during the creation of the signature. So basically evaluating this fx, that should be easy. And when I say easy, I mean fast.